In this lesson, we're going to go ahead and cover the rest of Section 7.2. In Part 1 of Section 7.2, we talked about multiplying radicals. So this will be considered Part 2 of Section 7.2, which involves dividing radicals. And so I've given you a principle that we need to consider when we divide radicals. And it basically says this: if we have two radicals, same root, different numbers, and the denominator cannot be 0, so in this case we've said, in this particular example, b cannot be 0, then really what we have here is two ways of writing division. We could think of it as two separate radicals being divided. So what we're told here basically is the division of two separate radicals could be thought of as one single radical of the fraction represented by, in this case, a and b, or we call these the radicands, the number of numbers underneath the radical. And interestingly enough, it works the other way as well. If we have one radical, whatever root that is, of a fraction, if it helps us, we could separate this into two different radicals being divided. So I wanted to show you how these two really are interchangeable. Depending on the problem that we're given, it will make sense to possibly change from one look to the other to make it easier to do the division. So with that said, let's look at some examples like you'll see on your homework. For example, in this particular problem, I think it's always a good idea to take a look at, so I think it's good, it's a good practice to get into, to just take a look at the numbers in the numerator and the denominator, maybe just for temporarily ignore the radical signs and see if you have a fraction that could be simplified into just a single monomial expression. And that's the case here because 12 is evenly divisible by 3. 12 divided by 3, of course, is 4. And we can also consolidate these two different x's that are being divided because we have a rule that says division of like bases means we subtract exponents, and x to the 4 minus 1 power, of course, is x to the third. So here's one of those cases where I was given two different radicals being divided, but it's going to be easier to think of simplifying this as just one single fraction underneath the radical, because as it turns out, I'm actually not going to be simplifying a fraction at all, because this fraction simplifies into 4x to the third. And now I'm basically doing what we were doing in the previous lesson. How can I simplify the radical, the square root of 4x to the third? Well, I'm going to use the perfect square root factor, 4x squared, times the non-perfect square root factor, square root of x. Those two multiplied together would equal the square root of 4x cubed. But in simplified form, the square root of 4x squared is really 2x. And this other radical, square root of x, cannot be simplified. So that ends up being my answer to our first example. Okay? And this problem is very similar because if I notice these numbers, 128 is divisible by 2 evenly. I can consolidate these two different x's being divided using the principle of division of like bases, like we did previously. Same thing for the y's. So really, I'm better off thinking of this, instead of two separate radicals, just think of the cube root of the fraction. 128x to the 7, y to the third over 2x squared, because then I'm actually going to be doing the cube root of 64x to the fifth, y to the second. Okay? And now I'm back to where we were previously. Let's think of two cube root factors that would multiply together to equal this, but again, the key is using a perfect cube root expression that simplifies. As it turns out, 64 is a perfect cube number, so I'm going to put it with the group that I call the perfects. X to the fifth is not a perfect cube variable, but it has a perfect cube variable in it, x to the third, and I can multiply that times x squared to make it equal x to the fifth. Unfortunately, I can't do anything with y squared. 3 doesn't divide into 2. There's no way to break y squared up into anything that I can divide 3 into. So we are ready to simplify this left radical. The cube root of 64 is 4. The cube root of x to the third is x. And then we're going to multiply by this radical cube root of x squared, y squared, to get to our final answer. Okay. Well, in some problems, reducing and then simplifying the radical is not possible. Like in this case with letter A, x is not divisible by 2, so it doesn't really help me to rewrite this problem as the square root of x over 2. That is of no benefit to me. And my directions tell me to rationalize the denominators, and that's just another way of saying show this simplified form using a denominator that does not have a radical in it. Remove the radical from the denominator. For square roots, that's pretty easy. I'm just going to multiply by whatever the radical is in the denominator. And I'm going to multiply both the top of the fraction and the bottom. So in essence, I'm multiplying by 1. Any number, and that includes radicals, any number divided by itself is just 1. So always remember, you're really multiplying by a fraction that equals 1, but it will just be whatever the radical in the denominator is over itself. Okay, multiplying numerators together, square root of 2x. Denominators together, the square root of 2 times the square root of 2 is just 2. Anytime you multiply a radical times itself, the result will be what we call the radicand, or the number underneath the radical. And then if I could simplify the numerator, I would, but there is no way to simplify the square root of 2x. I can't cancel because I can't divide non-radical into radical, so I'm done. That's the answer for letter A. Letter B is very similar. It's a square root, so first of all, I guess it's a good reminder, just double check, and if you can't reduce, like for example, 3 is not divisible by 5 evenly, so I'm going to rationalize by multiplying by the radical in the denominator. So the top and the bottom of this fraction will be multiplied by square root of 5xy cubed, and the result, the numerator, is going to be the square root of 15x squared y to the fifth, and then the denominator, once again, remember, any radical times itself should just equal the radicand, the expression underneath the radical. Okay, I think we'll go to the next slide to continue this thought. The square root of x squared y to the fifth. 15 x squared y to the fifth. Sorry about that. And that's divided by 5xy cubed. Since I can simplify this radical, I need to do that, so we've been doing quite a bit of this. Let's think of a perfect radical square root times a non-perfect. Starting with the number 15, it does not have a perfect square root. It also does not have a perfect square root factor. So that means I'm going to put it over here, not able to be simplified. X squared can be simplified because 2 does divide into 2. Y to the 5th, well, y to the 5th itself isn't a perfect square variable, but if I write it like this, I can at least think of it as y to the 4th, which is a perfect square. 2 does divide into 4, and then I'll put y over here to make it equal. Okay, continue simplifying in the numerator. The square root of x squared is x. The square root of y to the 4th is y squared. Okay, and then to finish this off, we're going to do some what you might think of as reducing. Now, not counting anything under the radical. We can't reduce under here, but the expression outside of the radical, for example, do you notice that these x's would cancel each other? X divided by x is just 1. I can divide y squared into these variables, y squared into itself, and y squared into y cubed would make this just 1. So here's my final answer. The square root of 15y over 5y. And that's reduced, simplified radical, and that would be my final answer. Okay. One more, just like this. On letter C, I'm going to multiply the top and the bottom of this fraction by the square root of 5x squared y. Notice I'm only supposed to rationalize denominators, and the number 9 is not under the radical, so there's no need to include that in my product. So when I multiply these together, I get 4 times the square root of 10x cubed y squared. And in the denominator, remember, if you multiply the radicals together, that should give you 5x squared y. We talked about a radical times itself and what the result is. Well, just think 5x squared y times 9, and that's 45x squared y. Okay, I think I'll go to another screen again. So 4 times 10x cubed y squared divided by 45x squared y. Okay, now let's see if we can simplify radicals. Perfect group times non-perfect group. Well, 10, let's start there. 10 does not have a perfect square root. It also does not have a perfect square root factor. 4, for example, doesn't divide into 10 evenly. 9, another perfect square root number, doesn't divide into 10 evenly. So square root of 10 will be over here not able to be simplified. For x to the 3rd, remember I'm going to do that as x squared, which is perfect, times not perfect x, and y squared is a perfect square root, or has a perfect square root because 2 divides into 2. Alright, so let's simplify this left radical, and we get 4xy square root of 10x over 45x squared y. Let's see if we can cancel. Notice the y's would cancel each other. Notice that if you divide x into both of these, x divided into itself is 1. X into x squared is x to the 1st. So that changes my final answer as 4 times the square root of 10x over 45x. Nothing else cancels, And so I'm left with this as my final answer, but I did what I was told to do. We now have a fraction with no radical in the denominator. Okay, so this is my answer to letter C of your notes, and this was the answer for letter B. Okay, almost done. You have a couple of problems where instead of rationalizing square roots, you have, in this case, letter D, you have a cube root, and then we'll look at what to do when you're rationalizing fourth root. First of all, I noticed that 5 isn't divisible by 4 evenly. I mean, it would produce a fraction or decimal. So I'm just going to break this up as the cube root of 5 divided by the cube root of 4y. Okay, now with cube roots and everything basically other than square roots, we can't just simply multiply by whatever the radical is in the denominator. Now when that was a square root, that's exactly what we did. For square roots, we just looked at the radical in the denominator and we multiplied by it, top and bottom. Okay, take a look again at those 3 examples. Notice that's what we did to rationalize when it's a square root. Well, for other roots, we're going to have to think a little bit. We're going to have to multiply by something, and I'm going to focus on the denominator first. I'm going to have to multiply this cube root of 4y by some cube root so that when I'm finished multiplying, I will have a perfect cube root expression, an expression that has a perfect cube root. For example, remember your perfect cube numbers, the numbers that have perfect cube roots, like 8. Well, if I could just make this become the cube root of 8, that would be easy to simplify, and I can get rid of the radical. The cube root of 8 is 2. To get there, I'm going to have to multiply the cube root of 4 times the cube root of 2. Okay, so your thinking now is you've got to think of something to multiply by to create a perfect, in this case, perfect cube root expression. Okay, so now let's move on to the y. If this were just y to the third, it'd be great because the cube root of y to the third is just y. Well, to make it equal y to the third, I'm going to have to multiply y times y squared. So I found what needs to multiply top and bottom of the fraction. Okay, so now I can go ahead and multiply the numerators together, and that will be the cube root of 10y squared. Now, there's no reason, again, rationalizing means remove the radical from the denominator. Well, that's going to be easy to do now because the cube root of 8 is 2. Cube root of y to the third is y. So let's just go ahead and write this as 2y. And I can't simplify the radical in the numerator. Can't cancel anything. This ends up being my final answer. It works the same way with fourth roots. Okay, so let me just set it up. I'm going to be multiplying top and bottom by some fourth root so that the result gives me a perfect fourth root, something that I can simplify without having to represent in radical form. So let's think about the fourth root numbers, the numbers that have fourth roots. 2 to the fourth is 16. Okay, so I'm going to multiply the fourth root of 4 times the fourth root of 4. The result is the fourth root of 16, which is has a perfect fourth root. We just found it. It's 2. Well, if I multiply by the fourth root of 4 on the bottom, I also have to multiply by that on the top. Remember, you're always just multiplying by 1, essentially. And so the numerator becomes the fourth root of 12. Okay? So now let's write the fourth root of 16 in simplified form, which is 2. And that gives us, we can't simplify the 4 through the 12, and so that ends up being our final answer. Okay, and that takes care of our examples, the class notes for division of radicals. And so if you have any questions, just send me an email or let me know in class tomorrow.